Okay, so this is our a tutorial. It's all about the chemical equilibria. And the chemical equilibria, first thing to know to get to the chemical equilibria is to know that a chemical reaction is happening or chemical reaction is occurring in this process, and that reaction is, what is the another, can anybody tell me what is the another condition that we should know about? The chemical reaction is occurring. What is the most important second criteria for any reaction to occur or to attain equilibrium? Anybody? Anyone? Hello, can you hear me?
Yes.
Okay, so you can just talk. I mean, I'm not saying that you have to correct. You make mistake there so that I can correct you. So what is the another important criteria? First of all, there should be a reaction going on. Second criteria is that it should be a both-way reaction. It should be a both-way reaction. That means there should be a arrow on the right hand, forward arrow, backward arrow. That means two reactions are going at the same time. Ammonia is being dissociated to nitrogen, hydrogen, and nitrogen, hydrogen is being combined to produce the ammonia at the same time in the same reaction vessel, in the same container at the same time. Right, so that is if it is not, if it is a single arrow like this, then it is, there is not an equilibrium, it will not be an equilibrium. How? That is HCl and sodium hydroxide. HCl and sodium hydroxide. Okay, so there will be sodium chloride and water, like that. There are many others, but this is one of them. And this one criteria, I am telling you that what's the criteria. So here, what is the difference between them? This is a strong acid and strong base. Strong acid, strong base, they will just go forward the reaction, they'll finish up the reaction, that's it. They will, I mean, so the thing is, strong acid, strong base, they do not produce any reversible reaction. There is no reversible reaction between strong acid, strong, or sometimes like you burn some fuel, right? You burn some fuel in a container. Let's say that how you take a container, strong container, put some petrol inside and light it up, right? It will burn inside the container. So will it come back to petrol again? No, it doesn't, right? There is all smoke inside. There is no petrol anymore. So explosive reaction or burning, this type of thing, they will, explosive reaction means you put some explosion, the firecrackers, right? The firecrackers, you light it up and then it, boom, it bursts up. It does not have any, it does not come back to that solid powder anymore. Firecrackers, there are solid powders inside. Many other gunpowder, aluminium, magnesium, many things inside. That is why they're different color. So it does not come back to the powder again. There is no both-way reaction. There are only forward reaction. That is, either it's burning, is producing heat, it is producing light, and this thing. So remember always that if there is, it does not have this type of both-way arrow in between them, that is not a both-way reaction, or it is not it will not attain equilibrium ever. But the good thing is, most of the organic reaction, organic organic reaction, what is organic reaction? Does anybody? I know that you're not supposed to know because we haven't studied the organic thing yet. But does anybody has any idea? Do you have any idea that what an organic reaction could be? What's organic? Vanessa?
I'm not sure.
Okay, Noor.
Reactions with natural
What?
compound.
Natural compound. All right, I accept that. Chammo, do you have any idea of what is organic compound? Chammo, we cannot hear you. Anyway, Bilal, do you eat organic food in your hometown, home country? So organic, there is a nowadays. Okay. So nowadays we know that organic, there is a lot of enthusiasm going on about organic. Actually, is good organic product that we eat organic product. But for our chemistry purpose, we will call organic a certain type of things, right? I cannot see the chat box, so I can, but I think somebody sent. I'm not going there again. Okay, so organic, and this will be fun actually. That's why I wanted to ask you that. Do you have any idea, or because week 9 onward we will start organic, and then I wanted to know that if you have any idea, so from where should I start? So I now know that I can start and it will be helpful for me to cover the things. So, and the lab, believe me, the organic labs are much more colorful and much more interesting. Anyway, so that will be our lab. Last 2 labs are organic. I don't know. So these 2 things. So for most of the organic reaction that is happening in our body or in the nature are reversible reaction. Most of the reaction are reversible reaction. And then you'll be amazed to know that some of the reaction that is started at the beginning of the universe and it has not attained the equilibrium yet. It's going on. It's going on. Haven't probably till the end of the day it will not attain the equilibrium. So there are some things. There is quite interesting thing actually. Probably you will know more about when you grow up. I mean, you have grown up, but when you go to higher education. Okay, so these are the worked example, and I hope that you have gone through all of these. The self-testing question are very similar to these actually, what we have done, I mean, in the worked example. So first of all, the question number 1 says that which statement correctly describes a chemical reaction at equilibrium? That describe the chemical reaction at equilibrium. So is it option A, is it a characteristic for the reaction that attain the equilibrium? All right. The option A says the concentration of the product and reactant are equal. Is it? Concentration of the product and a reactant are equal. Let's say, I delete this thing. Okay, concentration of A and B, A plus B, and it produces C and D. All right, it produces C and D. Why is this thing coming up? Okay, whatever. A plus B, C and D. Okay, A plus B and C, let's say for simplicity, producing C. So in the reaction, I mean, when it reaches to the equilibrium, K alpha, let's say, whether A and B concentration of A is equal to B is equal to C, is it? Concentration of A is equal to B is equal to C. Can it be? No, it is not. It depends on what is the initial concentration we started with, right? And of course, with the stoichiometric ratio, the number of moles they are reacting to each other. It depends on that. It can be like 2, it can be 3. So this thing will be 3 times than A1, right? So it does not matter what is the concentration of A, B, and C. it is not equal to each other. Option B says the concentration of the products and reactants remained unchanged. Whatever the concentration that we started with, right, in the reaction, A, and let's say that it attained X concentration, it attained Y concentration, it attained Z concentration at the equilibrium. It should be said at the equilibrium, right? At equilibrium, yeah, at equilibrium. So if the reaction is X, Y, and Z, then it will always be X, Y, and Z unless you change the external factor. External factor is you heat it up, or you put some ice to it, or remove the heat, or pressurize it. So otherwise it will always be the same. The rate of forward reaction is less than the no. The forward and backward rate will be always same. And then at equilibrium, the rate that is going to right side and coming back to left side is always the same. Question number 2 says, the reaction between nitrogen and hydrogen reaches a dynamic equilibrium. So my question is, why it is called dynamic equilibrium? Can anybody please? What is the dynamic equilibrium? Eric? You know, students hate me because I call names, but still I like to do that. Yeah, Eric, what is dynamic equilibrium?
I'm not sure.
Okay. I take your answer. I'm not blaming you, I'm not saying, but at least you say that you're not sure, so that I know that you don't know, so I can tell you. If nobody talks, then I think, okay, do they know or they don't know? So Brenda, do you know what is dynamic equilibrium?
Reversible reaction.
That is at equilibrium, right? Reversible reaction means at some time there will be forward and backward, but why do you call it dynamic?
Because it is at the same rate.
Yep, that means the reaction is reversible at the same time, but it is not stopped. It is going on. Do you remember the last class that we saw the treadmill? One hippo is running on the bear or hippo something running on the treadmill. That means it is at the same stage. They are staying at the same. His body is to the same point, but it is continuing. The reaction is continuing. So that is why it is called dynamic, but it is an equilibrium. Okay. So which of the following statement about the dynamic equilibrium is not true? The forward rate, option A, the forward rate of reaction is equal to the backward rate of the reaction. Oh, it's not true. Not true, yeah. So it is true. That's why I say that why it is. It is true because the rate is equal. If let's say rate is RF, I think last class I was talking, RF is forward rate and RB is backward rate. It depends on how you what do you call it, express or put the reaction. If somebody say that my reaction is NH3, right, and then the reaction is going this way, producing nitrogen and hydrogen. So in that case, it will be forward reaction. The forward rate of the reaction is producing nitrogen and hydrogen. But for this case, so it depends on how you put the reaction or how you express the reaction, how you're writing the reaction. Or okay, so nitrogen and hydrogen producing ammonia. So the forward rate and backward rate is equal. It is true. The concentration of the product and reactant do not change. Yes, at equilibrium, the concentration do not change. So this is true as well. The concentration of the product and reactants are equal. No, it's not. The product and reactants, it doesn't have to be equal. That means all of them has to be one concentration, one concentration, one concentration. No, it's not. It's not true. It doesn't, it is not required as well. So C is the correct answer. Who has question number 3? The equilibrium can be approached from either side. So yeah, we know that we just wrote it this way. So it can achieve from any side, means if you put nitrogen and hydrogen, it will produce ammonia, and then after you produce ammonia, then it will at some point it will be stable. That is the equilibrium. Or if you put ammonia in the system or in the jar or in the reaction vessel, right? So ammonia will at the beginning there is only ammonia, nothing else. So it will start to dissociate, and then nitrogen, hydrogen will be produced. After nitrogen, hydrogen will be produced, then there will be equilibrium. So that's why that either side, from all direction, the equilibrium can be achieved. Question number 3 says that which of the properties listed below are characteristics of a gaseous system in dynamic equilibrium? Sorry. So there are 3 options are given, that the concentration of reactant are equal to the concentration of product, right? Concentration of reactants are equal to the concentration of the product. It's not. Which of the properties listed below are characteristic of a gaseous system in dynamic equilibrium? Okay, so the concentrations of reactant are equal to the concentration of the product is not. It is whether it's a gaseous system or aqueous system, it's the same thing. So it is not the characteristic. The concentration of reactants and product remain constant. Yes. The reaction of forward reaction is equal to the rate of the reverse reaction. Yes, this is true. So 2 and 3 are the correct answer. Consider the following equilibrium: carbon, hydrogen, water is gas, so it should be vapor, right? So it says vapor. Carbon is solid, water vapor or gaseous water, producing nitric oxide, NO, and hydrogen gas. The K value is 0.16. At equilibrium, there are 0.6 mole of carbon, 0.3 moles of water, and 0.32 mole of nitric oxide in 1 liter of flask. What is the equilibrium for hydrogen? So from this reaction equilibrium, we can find it will be nitric oxide and hydrogen gas over water vapor, right? Water vapor, but it will not, carbon will not be considered because it is solid. So since it is solid, it will not be considered. And if we just put the value in, this number of moles are here, but it is in 1 liter flask, so mole and molarity become similar or same because of number volume is same. I mean volume is 1. We can just put in the values here, and then we will find 0.15 molar should be. Now K value, I have to plug in the K value from here so that we find what is the hydrogen concentration. Question number 5, it says that bromine and hydrogen react to form hydrogen bromide as the following reversible reaction equation. Hydrogen and bromine, 2 hydrogen bromide is being formed, and all of our gaseous system, all our gaseous system. So we have to consider all of them together. A mixture of 0.682 mole of hydrogen bromine combined in a reaction vessel with a volume of 2 liter. Now the volume is not 1 liter anymore, so we have to divide by 2 to get the concentration mole per liter, that is molarity, right? At equilibrium, there are 566 mole of hydrogen present. All right. What is the amount of bromine in mole present in the reaction vessel at equilibrium? So here what is saying that we started with this amount of hydrogen and this amount of bromine. Okay, started, that means at the initial point, ICE table. We have to produce ICE table because at equilibrium, only hydrogen gas, concentration of hydrogen gas is given, not the bromine or not the hydrogen bromide concentration are given at equilibrium. So we only know the concentration of hydrogen in the at equilibrium. We have to know the concentration of bromine and hydrogen bromide at equilibrium as well, because this Kc value depends on the equilibrium concentration, not at the initial concentration, and that is why we have to do the ICE table. So ICE table is 0.682 for hydrogen, and for bromine it is 0.44. So initially, what will be the concentration of hydrogen bromide? It will be 0, right? It will be 0. At initial concentration, it is 0. But now it says that at equilibrium, when we reached, there are 0.566 mole of hydrogen present. This column is for hydrogen. This column is for bromine. All right. So at equilibrium, this is 0.566 mole of hydrogen is remaining. How much hydrogen has been used up? How much hydrogen has been used up? Can we find? We already have it, but we need to find out the bromine and HBr. So that is why we need to find out what is the change. That means what was used for this purpose. So 0.682 minus 0.566, it is 0.116. 116 moles of hydrogen was used. And now if 0.116 mole of hydrogen is used, how many moles of bromine will be used? Any idea? Do you have any idea how many moles of bromine will be used?
No.
Say.
Okay. Yeah, because this is 1:1 reaction, right? This is 1:1 reaction. 1 mole of hydrogen is reacting with 1 mole of bromine. Right? Here it is 1 mole. I mean, there is 1 mole here. That is why it is not written. Right? This is 1 mole here. That's what I need to do. But here is 2 moles. This is 2 moles of hydrogen bromide that is produced. So if I used up 1 mole of hydrogen, for sure I will need 1 mole of bromine. If I use 2 moles, I will need 2 moles of bromine. If 0.1 mole of hydrogen, I will need 0.1 mole of bromine. Right? So if I used up 0.116 moles of hydrogen, I will also use 0.116 moles of bromine will be used. And then the balance is what remaining in the equilibrium. All right, so 0.44 minus 0.116. So 0.3224 moles. The number of the moles, number of moles are remaining here. Now at equilibrium, it is 0 for now. We come to hydrogen bromide. Yeah. So at the beginning, when I mix hydrogen and bromine, there was nothing, no hydrogen bromide produced. So it was 0. But when there is 0.116 moles of hydrogen and bromine was reacted, since it is 1:2 reaction, I will have 0.226. 116 times 2 is how many? 0.116 times 2 is 232 moles. 232 moles of hydrogen bromide I will have at the equilibrium produced, and this is positive sign. Of course, this is negative. This is negative sign. So I will have this. Now we go and check the equilibrium concentration, constant. So Kc is, or K is concentration of hydrogen bromide over concentration of hydrogen and concentration of bromine, right? So we can just plug in the values. 232 over 0.566 times 324. Yeah, 324. Oh, sorry, made a mistake. We have to convert it to concentration. Yeah, concentration. So this is a number of moles. So we have to convert it to concentration. So we have to divide by 2 the volume. Only then we will get the concentration. All right. So only then we will get the concentration, and then that value we will put it here. In that case, you will find the value for this is 324. The 324. What is the amount of bromine in mole present in the reaction vessel at equilibrium? Oh, it doesn't want the concentration, but it's good that I discuss the whole thing. All right. So this is what number of moles. You find it already. But in further, if it says that what is the concentration, K equilibrium constant for this reaction, so you can find from this way, right? Okay, so now question number 6, it says that given the so far, do you have any question? Anyone has any question? No question? Good. Okay, so given the following information, chlorine is producing 2 chloride at 1100 degrees centigrade, right? What would be the numerical value of the equilibrium constant for the reaction when the reaction is from the other way around? So we are producing, for this reaction number 1, I think it's better to give the number, reaction number. Yeah, it is a good idea to put the reaction number so that it is students are not confused. So in a reaction number 1, chlorine gas is being is dissociated and produces 2 chloride atoms, gaseous form, and again in the reaction 2 chloride gas atoms collided or comes together to produce a chlorine diatomic chlorine gas molecule. So what would be the numerical value of the equilibrium constant for the reaction? So we know that let's say this is K1, right? And this is K2. Equilibrium constant for number 2 reaction is K2. Number 2, the reaction is inverse of number 1 reaction, right? So number 2 reaction is inverse of number 2 reaction. So K2 will be inverse for K1. So 1 over K2, K1 will be equal to K2. So if we take this one, inverse of this, so this is K, 1 over K, that means 1 over this figure, we will get this value, 1.13 or 8.85 times 10 negative fifth. So this will be the value for this. Question number 7 says that chlorine molecules can decompose into chlorine atom according to the equation, right? The equilibrium constant for this reaction is 1.1 times 10 negative 6 molar at 1100 degrees centigrade. This implies that chlorine molecule decompose very slowly at 1100 degrees centigrade. This is the equilibrium constant for this reaction. Can you imagine how small this is? This figure 0.1234567 So this is the 1 in fact. So this is the value. How many zeros? 3, 3, 6, 7 zeros in front of 1. Yes, it is. It is decomposing, but it does not decompose. It dissociate, right? It dissociate to chloride atom. From chlorine molecule to chloride atom, it dissociate. So it's not the correct answer. B says that negligible percentage of chlorine molecule decompose at 1100 degrees centigrade. Since it is a very small number, very small number, so we can comfortably say is that yes, it's true that a very negligible, it's very small amount, even at 1100 degrees centigrade, that means very high temperature. A small amount of this chlorine gas will be decomposed, dissociated. When heated to 1100 degrees centigrade, chlorine molecules begin to split up. It is not starting to begin to split up. It started, but it is continuing there. All right, it is going on there. Chlorine is a very unreactive at room temperature. No, it's not true. Chlorine is a very poisonous gas at room temperature itself. Question number 8 says that hydrogen can be produced by the reaction methane and water vapor. When they are actually comes together, the carbon monoxide and hydrogen gas will be produced. And this is exothermic or endothermic reaction. I forgot. Can anybody help me? Is it exothermic reaction or endothermic reaction?
Endo.
Yes, is an endothermic reaction. So that means when this hydrogen del H positive, that means this positive value is here. We are adding this, whatever positive, negative, we are adding to the reactant side. So when it is positive here, del H, that means we are providing heat. And that is why it is endothermic. If it is an exothermic reaction, however, it will be negative. That means we are adding, negative means in this side is negative, so that side it will be positive, right? That means it is releasing heat, the reaction. So, this is the explanation. If you want to remember in that way, you can. But if you want to remember in that way, that positive means endo, that means we have to provide heat, and that's it. Anything else is exothermic. So that way also can, whatever is easier for you. Hydrogen can be produced by the reaction in this way. Which one of the following will increase the equilibrium yield of hydrogen? What do we do in this reaction that it will increase the hydrogen production? What will increase the hydrogen production? Increase the total pressure of the reaction system. If we increase the total pressure, what will happen? According to Le-Chatelier's principle, the reaction will move towards where it has fewer number of moles or fewer number of particles if we increase the pressure in the vessel, right? So which side it has fewer particles? This is 1, 1, 2, 1 plus 1, 2. Here 1 plus 3, 4. Right, this is 2, this is 4. Is it clear to you that this is number 3, 3 parts of hydrogen and 1 part of carbon monoxide, or 3 moles of hydrogen, 1 mole of carbon monoxide, whichever way is easier for you to understand. So there are 4 parts on right side, that is product side, then 2 parts in the reactant side. So if I increase the pressure, of course it will move towards the reactant side. Right, because where it is, it can have smaller volume of many things small. So it is not helping. Increasing the total pressure is not helping to produce the hydrogen gas. Decreasing the concentration of water vapor. If I decrease the concentration of water vapor, it is not helping as well, because decreasing the water vapor, so you are decreasing the concentration of water, and we know that it depends on the concentration as well. The higher the concentration, that means Le-Chatelier's principle, it will move towards the forward reaction. If I increase higher concentration of this gas or this gas, so the reaction will go forward. So if I use this higher concentration of either of them, then more hydrogen will be produced. When I'm decreasing it, this is not producing more hydrogen, rather it is the inverse effect is happening there. Removing carbon monoxide from the system as it produced. So if I remove the carbon monoxide when it is producing, yes, then what I'm doing is, according to Le-Chatelier's principle, the reaction, the equilibrium will move forward, right? Because here there is a void, there is a vacuum created. If I remove the carbon monoxide, the vacuum is being created. So to cover this vacuum, or to what is called fill up the vacuum, right? More carbon monoxide will be produced. This methane, CH4 and H2O, hydrogen, water vapor, they will react faster to produce more carbon monoxide to fill up the vacuum. But it cannot only produce carbon monoxide. In the same process, more hydrogen should be produced as well. And that is how we can get more hydrogen if we remove the carbon monoxide from there. So this is the technique actually was done by Haber process. You remember the last slide of last class that he revolutionized the production of ammonia in 1918. So that time he removed as the ammonia was produced, he was removing the ammonia. So more ammonia was produced. Decreasing the temperature of the system. If the temperature is decreased, then it is not produced because it's endothermic, so it needs more heat to be produced, to be given to the system. So decreasing the temperature will not help. Question number 9 says the following reaction reaches equilibrium in a closed reaction vessel at 200 degrees centigrade. All right. The following reaction reaches equilibrium in a closed reaction vessel at 200 degrees centigrade. Carbon monoxide, gas, then water, hydrogen in gaseous form is producing methane, gas, and water vapor. And it is a exothermic reaction. It is producing quite much of heat. Why it is happening? So which of the following actions causes the reaction to produce from left to right in order to restore equilibrium? Okay, let's say that the equilibrium was disturbed. They attained the equilibrium, but the equilibrium was disturbed with something, and then reaction causes the reaction to proceed from left to right in order to the reaction it was having an equilibrium, it was quite calm, and then the reaction was going on equilibrium, but somehow it was got disturbed. If the reaction is disturbed, how this reaction can be moved forward to produce more methane and water? Option A, increasing the volume of the container, holding the temperature constant, right? If we increase the volume of this container, what will happen if we increase the volume? Can anybody tell me, if I increase the volume, then pressure is increasing or decreasing?
Decrease.
Yeah. So let's say, just to put some graphic here, and how? Okay, let's say that I have this big container, right? I have this big container, and this is screw. There is a cap or something. Let's say this cap, and this gas, that is carbon monoxide and hydrogen gas inside. I channel this gas to another container with this big, right? And this is a cap, this screwed on from top. So it is 50 milliliter. I make it 500 milliliter, right? So if the container size increases, the pressure decreases because they have more place to play around inside the container. And if the pressure is decreased, what will happen according to Lorentz principle? Here there is 3 plus 1, 4 parts on left side, and it is 2 parts. So the reaction will move towards the left side where there is more parts available. So it is not going forward, it is not going to right side, it is going to left side, the reaction. Option B says that adding some methane gas to the system with volume and temperature held constant. Of course not. If I add methane, where this methane is going to go? Of course, it will go to the left side to produce more carbon monoxide and hydrogen gas. So both A and B are not correct. It's not a good strategy. Option C says decreasing the temperature, holding the pressure constant. Okay. If I decrease the temperature, but I keep the same pressure, then what? So same pressure means there is no change. Let's say, forget about the temperature. Pressure is same. That means whatever happened. If they are in the equilibrium, they are still in equilibrium at the same pressure. But suddenly I'm decreasing the temperature. I put some ice there around it, and then reducing the temperature. So what will happen is, since it's an exothermic reaction, so this exothermic reaction, the heat is removed from the system. So more thing is coming on, more heat will be produced. How the more heat will be produced? Of course, the reaction has to go forward. Only then the heat will be produced. So to produce more heat, the reaction will go forward. So C is the correct answer. Removing some carbon monoxide gas from the system will, no. If I remove this carbon monoxide, there is a void or a vacuum again. So to fill up the vacuum, more backward reaction is going on. All right, question number 10. In which of the following would the position of the equilibrium not be affected by a volume change at a constant temperature? we we do not change the temperature, but volume, we just change the volume, but temperature is constant. Although there is none of this is talking or giving us any hint about the endothermic or exothermic reaction or not, but only it's telling us that we keep the temperature constant, whatever temperature, exothermic or endothermic, doesn't matter. We do not give or take temperature from any of them, but we are just changing the volume. In this case, we see that A, it is 2 plus 1, 3 parts on this side. It is 2 on the right side, right? So it will be affected because there is different number of moles or different number of particles on the both sides. 2 plus 1, 3, and on the right side is 2. B is also is different number of particles. This is 1. On right side is 1 plus 1, 2. C, it is also 1 and 2. But D, I see that it is 1, 1, 2, 1, 1, 2. So D will not be affected. There will be no problem. If you increase the volume or decrease the volume or increase the pressure or decrease the pressure, does not matter. So D will not be perturbed. Question 11 says, consider the reaction. Iron plus water, of course in vapor form. Gas means water is heated, yeah? Water is how water becomes a gas. Of course, it has to be heated. So hydrogen and first ferric oxide, actually iron 3 oxide will be produced. So when the total pressure is increased, if the pressure is increased, what will happen? More hydrogen will be produced, more iron will be produced. What will happen? Of course, if the pressure is produced, more, that means more hydrogen will be produced, isn't it? Because it is 4 plus 1, it is 5 on right side, and it is 7 on left side. 3 plus 4, 7. So more pressure means it will go to the less number of moles, isn't it? So more hydrogen will be produced. Question number 12. Any question? Hello? You guys are not listening, yeah?
No, sir. We just have to have time to process.
What process?
Yes, sir. We need time to process.
Oh, okay. That's good. That is good. I like that you take time to process or think about it. But what I said for this question number 11 is not true. Nobody object. Nobody said anything. That's why I was surprised that are you listening or not? Actually, heat is solid, right? This is solid. This is also solid. So solid is not considered. Whatever is, doesn't matter what's the concentration, number of moles in front or not, doesn't matter. The solid, as I say, that it doesn't have it doesn't contribute to the vapor pressure, so it doesn't matter. So that is why here is 4. Here is 4 as well for the gaseous particles or gaseous species. For the gaseous species, okay? So that means it does not matter if you change the pressure or not, it is still the same. On both sides, it is 4 and 4. Here is 4, here it is 4 as well. All right, doesn't matter it is 3 or 1 because they are solid. Yes, S means solid form. So you change the temperature, it doesn't matter. It will not, no change occur. It will not change occur. So that's why first time I said wrong and I was surprised nobody objected. Question number 12, it says that give the equilibrium reaction in given the equilibrium reaction in a closed system, hydrogen and iodine in a gas form plus heat, hydrogen are produced. what will be the result of an increase in temperature? This endothermic reaction, so more hydrogen iodide produced, right? More hydrogen iodide will be produced, but how more hydrogen iodide is produced? Of course, hydrogen and iodine has to be reduced from the system. Only then, if hydrogen and iodine remove or reduced from the system, so that hydrogen iodide will be produced, because it's an endothermic reaction. So you put more heat, it is favorable for the reaction to occur. Question number 13. The graph shows the concentrations over time for the system. Carbon monoxide, gaseous form, hydrogen, gaseous form, and then methanol, also gaseous form, right? So carbon monoxide and hydrogen, both are gaseous, producing methanol. Okay, for this, let me take this opportunity to talk more. So carbon monoxide, right? This carbon monoxide, it is different from carbon dioxide. We know, right? Why is happening? Okay, carbon dioxide is this. And do you know that carbon dioxide is a problem for our greenhouse gas or global warming? We know, right? That because the carbon dioxide is increasing, so that is why we say that we have to reduce the carbon removing by the, oh, you already have done the project, so all of you know. And in some cities in the world, recently in India, in Delhi, I think, and for some time it is in Amsterdam, probably, they are using some big fan absorber, they call it absorber, to take the carbon dioxide from the atmosphere and catch it somehow. Carbon dioxide. What do you do that carbon dioxide? I mean, you catch it. Where do you keep it? You keep it in a bottle. It is not the Aladdin's genie that you can keep it in a bottle for as long as you want. Right? It is a gas, a material. You have to use it, or what do you want to do with this? So another good research came out that carbon dioxide, if we can produce ethanol, right? CH3CH2OH, this is ethanol. Many of us know already, actually. I think all of us know. So this is ethanol, and this is used. Ethanol has a much more wider use in industrial case than methanol. Also, this ethanol used for biofuel, right? So if we can catch it and produce it to ethanol, then our global warming problem will be much more solved. If we can, then it's solved. But the problem is, it is not easy. It's carbon dioxide to catch and produce ethanol. There are a lot of research going on, and some of the scientists, they are successful in doing partly of it to convert this carbon dioxide to ethanol, because carbon dioxide is quite stable, right? Very stable molecule here. It's quite stable. It doesn't want to react with anything. Whereas carbon monoxide is reactive, and it is another property of carbon monoxide is it binds very good with hemoglobin of our blood. So those who smoke, or they are exposed to the smoke or exhaust system, they inhale a lot of carbon monoxide, and it is very hard to take out from the blood, because our hemoglobin binds is very nicely, very strongly it binds it. And the problem of the carbon monoxide is if it is too much, the concentration in a room, there is no smell, no taste, nothing. There is no changes in we will never, I mean, we will not even realize that it is not air, it is carbon monoxide. So what happens is people, those who succumb to this type of things, that don't even know that they are dying. That carbon monoxide, they burns the blood, and it is a, they just fall down and then die. That is the, okay, enough, right? Enough talking. Now go back to our problem of this tutorial. Okay, so this problem is saying that carbon monoxide we are producing to methanol, and for this carbon monoxide is reacting with hydrogen 1:2 reaction and then producing 1 mole of methanol. What is happening is we are starting 1:2, right? We are starting at the same number of moles of hydrogen and carbon monoxide. So you see that since we started from the same number of moles, right? Carbon monoxide is reducing this much, whereas hydrogen is reducing double of it, right? Double of that much of carbon dioxide, double of as of carbon monoxide, hydrogen is used up. But at T1, hydrogen shoots up like this, like going to the sky. So what happened here? Since I said on the lecture slide that when it shoots up like this, it means there is no change. I mean, there is a change, of course, but it's obvious that more hydrogen has been added to the system. More hydrogen at the same time, it added. How do we add the hydrogen to the system? What will happen is, then let's say that carbon and hydrogen, just to give you an example, I mean, probably a perspective. Okay, so this is another one. This is a reaction vessel. This is a closed system. This is a box. Okay, this is a box, and this is a cylinder. This is another cylinder. This is, I should have drawn it here. This is another cylinder. All right. So this is carbon monoxide. This is hydrogen. And this is methanol. All right. So how does I can add, and then at the same time, same moment, like it is 5 minutes. At fifth minute, what will happen is I'll just open this valve of hydrogen, right? So I will just open the valve here like this, and then at the same moment, because this is the high pressure gas inside the cylinder, the gas will go to the system. So that is why you see that it is at the same time at the exact 5th minute. And then after that, maybe for 30 seconds, I open the valve and then close the valve again. So at the same moment, more hydrogen gas is added to the system. And of course, after that, the reaction goes on and the hydrogen starts to reduce. By this time, methanol is being produced, because at the beginning, there was no methanol, zero at the beginning. So methanol starts to produce. And then when the hydrogen was removed, added again. So at this point, you can see that maybe here, it is quite like flat. This line is quite flat. So they were almost attaining the equilibrium at this moment, right? At this, just before T1, they almost attained the equilibrium. So it is, for industry, equilibrium is not good. All right, don't tell anyone. For industry, the equilibrium is not good. They don't want it to be equilibrium, because equilibrium means there is nothing happening, but industry need to spend money. Industry doesn't like that. They hate it actually. They want the outcome. So they don't want this equilibrium to occur. They want it to continuously produce the product. So once it was near to the equilibrium, they added more hydrogen. Yeah, they added more hydrogen to the system. And after that, you see the methanol started to increase, and then at the same, again, around the same T2, they were getting the equilibrium. They were achieving the equilibrium. All right. So what happened? They remove some of the methanol. It's not this simple, but just to give you an idea how. They removed some ethanol from the system. At the same time, how do they remove the ethanol? They just open the valve, ethanol goes to the container, they close the valve again. So ethanol goes and then they are not equilibrium, ethanol start to increase again, they reduce. So this is thing happening. So at point A, hydrogen was added, and point T2, methanol was removed from the system. Question number 14 says a concentration time graph for a reversible system is shown below. All right. So nitric oxide, chlorine, and nitrosyl chloride is being produced in NaCl, nitrosyl chloride. So what event occurred at time T to cause the exchange in the equilibrium concentration? At T, what happened? Nitric oxide was added to the system, right? Nitric oxide added to the system. So when nitric oxide is added, since it is 2:1 reaction, more nitric, twice as nitric oxide was NO, or nitric oxide was used as a chloride, because 1:2 reaction, and then nitrosyl chloride slowly increased in the system. And this is the same thing actually. It is question number 15 is also telling the same thing, so I'm not going to talk. All right, so first exam question. Before that, let me just take a quick break, and I'll be back by another 2-3 minutes. So if you have any question, please ask. All right, I'm back. So seems like you don't have any question. Okay, so now I'm going to, for past exam question, I'll not go through all, but few of them. If you have any specific question, you have problem with a specific question, please let me ask me so that I can discuss. Question number 1 is saying that 2 mole of nitrosyl bromide is introduced into a 5-liter vessel. So when there is this type of question, descriptive question, please consider all the number of figures. Okay, maybe some of them are, not all of them will be useful, but most of them will be useful. So it's better to list it down on the paper, that what are the values, number of moles of nitrosyl bromide, volume of the reaction vessel, temperature, all these things you write down so that you get a good, you don't miss anything. So 2 moles of nitrosyl bromide is introduced into a 5-liter vessel at a temperature of 350 Kelvin. The gas decomposed and reached equilibrium according to the reaction equation below. Right. At equilibrium, 1.5 mole of nitrosyl bromide remained. What is the expression of Kc? Kc, of course, is Kc or K, sometimes we can call it Kc. So it will be nitric oxide, right? Oh, sorry, it is nitric oxide here, NO, not NO2. But since the 2 moles, it will be squared or powered, and then bromine. Since bromine 2 is the atom number, so it will be there. So if it is left side on the left of that species, so it will be powered. Right side is not is as it is. Same goes for nitrosyl bromide, NOBr2, and 2 is powered. Right, so this is the expression of constant, and it says that calculate the concentration of the 3 gases in a container once equilibrium had been established by completing the following table. So when you are saying that completing the following table, please write it in the table, or when the table is given, please write it in the table. This is better for you, for us both. Calculate the concentration. Oh, okay, so at equilibrium, we started with 2 mole of nitrosyl bromide, right, at 5 liter of vessel. So 2/5 is the concentration, 2 moles per 5 liters. So that will be the concentration. And at equilibrium, we can find 0.4 moles, 0.4 molar concentration. And at equilibrium, 1.5 moles of nitrosyl bromide is remained. So equilibrium is 1.5 over 5. So it will be 0.35, is it? 1.5 over 5, 0.3 moles of 3 molar concentration of nitrosyl bromide is remained. So how much has been used? Of course, 0.1 moles has been used, right? 0.1 mole has been used of it. And then if 0.1 mole has been used, that is the negative one, how many moles of nitric oxide will be used? How many moles of nitric oxide do you think will be used? It will be the same because 2:2 reaction. 2 moles here, 2 moles here. So 2 moles of nitrosyl bromide will produce 2 moles. So 0.1 mole will be 0.1 molar as well. Right? And then, sorry, it is positive. And bromine is positive 0.05, sorry, because it is half of what being produced from that, from the reaction in the nitrosyl bromide. Right? 0.05 will be there. So it remains the same for the equilibrium. It remains the same for the equilibrium. Now, if we plug in these values here, we will find the Kc value. Question number B says that a 36.8 gram sample of dinitrogen tetroxide was heated in a closed flask of volume 16 liter. An equilibrium was established at a constant temperature according to the following reaction. Right, dinitrogen tetroxide were at equilibrium reaction. This produces nitrogen dioxide. The equilibrium mixture was found to contain 1.18 mole of dinitrogen tetroxide. The number of moles of dinitrogen tetroxide in the 36.8 gram sample, and also the calculate the number of moles of nitrogen dioxide in the equilibrium mixture and write the expression on it. So number of moles of nitrogen dioxide tetroxide, how many, what is the number of moles of dinitrogen tetroxide? We have to find the dinitrogen number of moles. Okay. My energy is going to be finished soon, so I have to finish faster. Number of moles of dinitrogen tetroxide. What will be the number of moles of dinitrogen tetroxide? How do we find it? It is 36.8 gram. 36.8 gram over, so just recall the week 1, week 2 things. How do we find the number of moles? Molar mass of nitrogen and 2 nitrogen times 2, nitrogen times 2, oxygen times 4, and that way we will find that 14 times 2, 16 times 4. By this way, okay, 14 times 2, I'm just rounding up, 16 times 4, a plus in between, of course, right? Oh, it's not plus into minus, plus in between. So that we find the number of moles is 0.4 mole. 0.4 mole for calculate the number of moles. Calculate the number of moles of nitrogen dioxide in the equilibrium mixture. In the equilibrium mixture, so we see that nitrogen dioxide is 1:2 reaction, right? For bromine to nitrogen dioxide, and nitric oxide is 1:2 reaction, but when this reaction, dinitrogen tetroxide is producing 2 moles of nitrogen dioxide. So how many moles will be left over? 0.4 we had started with, and then at equilibrium we see that 0.180 mole of nitrogen dioxide was remaining. So the rest had been broken, right? We started at 0.4, we started, and then at equilibrium this number of mole was remaining, so 0.22 was used, and of nitrogen dioxide, well, dinitrogen tetroxide, 0. Was used up, but since it is 1:2 reaction, so multiplied by 2, and then 0.44 moles of nitrogen dioxide will be produced at equilibrium mixture. Should be there, number of moles be there, and it is in 16 liter. So we can find at equilibrium, this is number of nitrogen dioxide, so divided by 16 liters, so we find the mole per liter, that's molarity, and 0.44 nitrogen dioxide divided by 16 to get the molarity of nitrogen dioxide. And then we just put the value in Kc is concentration of nitrogen dioxide power 2 power 2 by dinitrogen tetroxide. Okay, so this is we just need to put the values in and then we find the Kc value. I'm not going through this. This is the same thing. Question number 2A. And also the same thing, because it says that 1.5 moles of sulfur dioxide. So just to put it fastest way is sulfur dioxide and then oxygen. So if this type of question, the first thing you have to write the equation and then in the underneath the equation do the ICE table. All right. So this is best for you, for us as well, so that we understand, that you understand, and you have not you have done it by yourself, that because you understand the thing. So sulfur trioxide, right? Sulfur. Now we started with 1.5 moles sulfur dioxide and 2 moles of oxygen. 1.5 sulfur dioxide and 2 moles of oxygen and 2 liter of flask. So divided by 2 so that we find the number molarity, right? 0.75 moles and oxygen is 1 molar at 400 degrees. And then the final equilibrium mixture contain 0.5 moles of sulfur trioxide. So initially there is 0. But equilibrium, we do not know the change yet, but equilibrium, we see that there is 0.5 moles of sulfur trioxide is there, right? 0.5 moles of sulfur trioxide is there. So this is, we can find it from, we can roughly estimate from oxygen, but it is best that we estimate it from the same number of moles, because this is 2 moles, this is 2 moles as well. So if X mole or if 0.5 moles of sulfur trioxide is being produced, that means 0.5 moles of sulfur dioxide has to be used, right? So minus 0.5 moles should be used as well, right? Because it is a 1:1 reaction. Okay, and 0.5 moles of sulfur trioxide is being produced. Yes. So 0.5 moles over 2, because we are using this concentration. So this is how it is important about the unit. If you are using concentration molar, so use all for molar, otherwise it will be really messed up. So 0.25 molars here as well. So it will be negative 0.25, not 0.5, negative 25. And since it is 1:2 reaction, it will be half of that 0.25, that will be negative 0.125. So this is the rest. The rest will be 0.5 here. This will be 0.75 here. No, 0.87, sorry, 875 here. Now we got all the concentration. Just need to put the value in Kc so that we find the concentration. Is that okay? So far, anybody has question on this? No question. No shortlist principle to affect, explain your answer. So you can, these are the descriptive type question. So you have to explain. It's just not, sometimes students say increase or decrease or no change. Some I saw one student say like this, I mean, cross and cross change. So later I think it's why cross. So later I understand that he or she was trying to mean is no change, right? So this answer will not give you 2 marks. You have to explain why it is increased, why it is decreased, why it is no change. All right. So at least write 1-2 sentences. 2 marks. So better that you write 2 lines, 2 sentences. All right, so this is the same thing that we're asking, and here it is the activation energy here, and this is, oh, can I ask anybody, where are you guys? Erlin, are you there? Believe me, this is the last question I'm asking, and I'm calling your name for today. I will not ask anyone else.
Yes.
This is exothermic or endothermic reaction that you see on the screen now, whether it's exothermic, sulfur dioxide and oxygen, sulfur trioxide, exothermic or endothermic. There is, don't feel awkward that you cannot answer, because I'm sure that many of us cannot answer it. Jamod, are you there? Jamod is not there. Yeah. So what is exothermic or endothermic? Chelsea says exo. Brian is typing. Brian, isn't it easier for you to just unmute and talk? Vanessa, what do you think? Exothermic or endothermic? Eric?
Exo.
Excellent.
Okay.
It's excellent.
Yes. Is exothermic. Why? Because we started here, let's say it was 0, right? When it is there, like we have sodium hydroxide and HCl in the room temperature or room in 2 different bottles, they are stable there. So we started from 0, and then the energy go up because they mix, and then the energy go down means it's going beyond where they started. It's not necessarily 0, but it started with a very low temperature. But when the product is going beyond or beneath the energy that we started with, that means they are releasing some energy. They are releasing some energy. And that is why it is an exothermic reaction. All right, so exothermic. So thank you. And do you think that the product is stable or unstable? Anybody? Is the product stable or unstable? For exothermic, the product is stable because it is releasing energy to produce. Okay, so I think this is it. Actually, this is all the descriptive question, and then here it is. Oh, I need to explain this thing. Okay, so this is the last one. Question number 4. In solution, pale yellow color, we will be doing this type of experiment in the next week, Thursday. In solution, pale yellow colored ferric and colorless thiocyanate ion from equilibrium with ferrous thiocyanate. Okay, so ferrous thiocyanate is red in color, it's blood red color, and we'll be seeing this later on. So this is a pale yellow color. This is colorless. When we mix them together, they become red color, blood red. And del H is negative, so it's an exothermic reaction. All right. A student investigates this reaction using separate samples of an equilibrium mixture in which significant quantities of ferric, thiocyanate, and ferrothiocyanate are present. In each case, changes are made as indicated in the table below. Complete the table by ticking, putting the ticks on the intensity of the red color of the solution and the concentration of iron once the new equilibrium has been established. So this is the reaction. This is the reaction that is happening, and if I add 1 drop of concentrated iron or ferric Fe3 aqueous in that solution, like all this thing in a beaker, right? I have taken iron thiosulfate and it produces ferrothisulfate in a beaker. And then I'm adding in that beaker 1 drop of this iron ferric ferric or Fe3. What will happen? In this case, the iron is added, so the reaction is going right or left. The reaction will proceed forward, right? Because the concentration of iron increases, so it becomes more red. It becomes more red. And iron at new equilibrium compared with the initial equilibrium will be increased. The concentration of iron, of course, it will, when it is going forward, this is increasing. And this is increasing means iron thiocyanate is increasing as well. So it will increase as well. Sample 2, 1 drop of concentrated solution of silver is added, which forms silver thiocyanate precipitate. So if I add 1 drop of in this beaker, right, I add silver something, all right, 1 drop of silver chloride, silver nitrate, all right, silver nitrate I added, and from there silver ion will come, the same silver, the ornament that we make. So this silver is coming. What will happen is that silver will go and bind with this thiocyanate, all right, and silver thiocyanate will be produced. So silver thiocyanate will produce means this thiocyanate is missing in action from this scenario, right? This thiocyanate is missing from this scenario. So thiocyanate is taken, consider that thiocyanate is taken down. It is taken down, that means there is a void created here. And then iron will be, this reaction will go backward to fill up this void. So the reaction become less red, right? The reaction becomes less red. The reaction will be less red in that. So more of this iron thiocyanate will be going to backward side. So, and then when it's going backward, the new equilibrium will be produced at some case. And when this equilibrium is produced, that means iron, the new equilibrium compared to the initial equilibrium will be decreased. Of course, iron will be decreased from this case. All right. So sample number 3. Addition of large volume of water. If I add more water in the beaker, just distilled water, the water, this is aqueous, this is aqueous, this is aqueous. So all of them are actually in the water. We have made the solution in the water. Now I am adding more. The common thing between them is water. So I'm adding more water into the beaker. Right? What will happen? All of them will be happy because water is their good friend. They have been there. But since I'm adding water, that means I'm increasing the volume. Volume increase means the reaction will shift to the more number of particle size. That is, the reaction will go backward. The reaction will go backward. And reaction goes backward means less red and less. Concentration of iron will also be reduced because it's going to backward side. Forward reaction is exothermic, so everything. So you have to draw the graph here, what is happening here. Final equilibrium, iron is increasing or decreasing, and when the water is added or heat is added, how the reaction will change. You have to draw the things. All right, so this is it, and then you can do this thing later on. Okay, I'm done. Do you have any question, anyone? Anyone has a question? Calling once, twice. No question. All right, so I'll see you on Monday, 2 p.m. again for the lecture 9. And of course, I'll see you for next lab. Right, all the best. Take care. Bye-bye. Thank you. Thank you.
Sir,
Yeah, Jesse.
what is the operation time of the student information center?
Sorry, what?
To create the student ID card.
I mean, your question is where the student center?
Yeah, and what time does it operate?
Oh, you can come from 8:30 till 5:30. They will be here, and it is in the main lobby. Do you? I mean, have you come to Swinburne right before?
No.
Oh, really? So,
Yeah.
are you coming for the lab?
Yes.
Oh, okay. So on Thursday, if you come, or you can come anytime this week. Oh, to find out today. Next week you can come, and then you just come in from the main gate. You enter from the main gate, and then come to the foyer at the main entrance. There will be glass door. You come in. The guards are sitting there taking temperature. Of course, you don't have to show anything. You just coming, and in you on your left. On your left or on your right?
Okay.
Oh, no, on your right, sorry, on your right. You pass by the guard, and in the big glass door, you come in. On your right, there is HQ is written. Or you can just ask, you just come into Swinburne, it's not that big, you can just come in, then you can see. Or, yeah.
Okay.
The main thing, yeah, you just come in the main foyer or main entrance, the glass door, come in there, take the temperature, scan the QR code, and then on your right side, it will be the student HQ. Or you can ask the guard.
Where shall we park?
There is a parking here in Swinburne. Anywhere you can park. There's a lot of empty space now because not many people coming. So a lot of empty space. You can park anywhere inside.
Okay. Okay. Thank you,
All
sir.
right. No problem.
Bye.
See you. Bye-bye.